Well, I trust you did well on your test in the last lesson. Students in here did fairly well. It's also noticeably brighter in here. All of a sudden, got the light fixed. Now it's slightly strange. All right, anyway, the students in here did very well. Hopefully you did as well. We do have an exam coming up next. No new material, just 2 days of review. We'll be reviewing today. We'll be reviewing again in lesson 129. And then lesson 130 is your quarter exam for you students. That's on Tuesday. We'll take your exam over chapters 13 through 18. So let's get an exam notes review section going and jot that first information down that you will want to study over chapters 13 through 18. Going all the way back to right after Christmas break, when we talked about rotary motion. We got to see rotary motion yesterday there at the Anchor Pack plant, right? See all those gears spinning and stuff. Rotary motion, right? And rotary motion, one word to define it would be spin, right? Rotary motion is essentially spinning motion. Motion where an object moves about its own internal axis. Make sure you know that term, rotary motion. With rotary motion, we measure the amount of turn as an angle. The amount of turn then is called the angular displacement. Right, that term out, angular displacement. It's the amount of turn or the angle of turn. In fact, how do we represent angular displacement? Theta rad. Right, put that with angular displacement. Okay, it's that amount of rotation. It's the amount of spin. It's an angle. It's theta rad. Measured, of course, in
per second. Nope.
Radians, right? Angular displacement, it's an angle, it's a radian. So radian values. Now, with most spinning objects, and we can attest to this, thinking of yesterday, right, as those different gears and parts were spinning, right, the amount of spin is really hard to define in just an angle, right, because it's spinning very quickly. Normally, we measure spins in terms of complete spins. What's a complete spin called? Well, its value is 2 pi radians, but a complete spin is called a revolution. So remember, this is where I was going with that. If we have revolutions, because that's usually what you would be given, convert revolutions to radians, multiply by 2 pi. Multiply by 2 pi. Spin rate. How fast something is spinning. We refer to that as more specifically, angular velocity, all right? Angular velocity, write that term down. The spin rate of an object. Angular displacement per unit time, but the spin rate of an object is called angular velocity. Do you remember what we represent that with? Omega. Some of us are very thankful we're reviewing on a Friday where you have all weekend to start looking this over. All right, so don't waste this weekend. Were you going down to Master Clubs Regional?
No, but I'm busy all weekend.
You're busy all weekend. Okay, well, squeeze some time for maybe looking this content over, because it's been a while, right? Chapter 13 feels like an awfully long time ago, mainly because we haven't needed to continue using it, right? A lot of physics has built on itself. That section kind of stood on its own, it almost felt like, and so makes it a little bit harder. So do look over, especially chapter 13. Angular velocity is that spin rate represented by omega, and angular velocity is measured in what units? Well, that'd be regular velocities, meters per second. This is a spin, so not meters, but radians per second. Radians per second. A change in angular velocity, that is, an object begins to spin faster or spin slower, is called change in angular velocity is called angular acceleration. It's a change in the spin rate. Something starts spinning faster or spinning slower. Angular acceleration. Represented by the Greek letter alpha. And it's measured in what units? Radians per second squared. For some objects, the spin rate is directly tied to a linear advance, like a wheel, for instance, right? As it rolls along the ground, it is both spinning and it is progressing linearly. And so we said if you wanted to track the linear velocity or the linear acceleration or even the linear displacement, right? You're on a merry-go-round and the merry-go-round is spinning. Well, you are moving forward as well. Your forward progression is directly tied to the spin rate of the object. So linear velocity, linear acceleration, linear displacement. If you want to know one of those three values and you know the angular, what did I say we had to do? Multiply by radius. Linear equals angular times radius. Michael's like, I think I got this. I'm feeling pretty good about this. And the lady's like, oh no. If you're watching and you feel like, oh no, okay, you're like, I'm with Audrey and Kendall here. Study. Okay, we're touching on these things so we can study over the weekend. Michael, don't get overconfident and blow the test because I thought I knew it. I didn't study. All right. Resistance to a change in rotary motion. An object is spinning, it tends to just keep on spinning unless something acts on it, right? Or something's not spinning, it tends to not spin unless something acts on it. The resistance to changing rotary motion is called rotational inertia. Rotational inertia, a resistance to changing rotary motion. Two factors affect the rotational inertia of a body. All right, first of all, the mass. If my little girls, they like to dance with daddy, okay? Dance, we call it. Bounce around, spin them around a little bit, okay? They spin more easily than my wife spins, okay? Just, it's fact, it's not a slam on anyone. It's easier to spin Chloe around or Renee around than it is to spin my wife around. It's even easier for me to spin them than it would be for my wife to spin me. Daddy don't spin too well. What was one reason why that would be the case? Mass, right? Greater mass is harder to start spinning. That said, once a greater mass has started spinning, it's hard to stop it spinning, right? That's the principle of the flywheel, remember, that was talked about in your book. It's a big, heavy disc that once you got it going, it tends to keep its motion, which keeps things working nice and smoothly. Okay, so mass affects rotational inertia, and then also the distribution of the mass. For instance, if we had Kendall put her arms out while we're trying to spin Kendall, that would be a little harder to get her spinning, and she would keep spinning a little bit longer that way, arms out, then arms in. So rotational inertia is affected by the mass and the distribution of the mass. Remember, we had the rods with the one rod was lighter, had less mass than the other. The one was really easy to spin back and forth. The other was harder to start spinning, and then once you started spinning one way, it's harder to stop that spin and get it back the other direction. Do you remember doing that with the brass rod and the cheap little aluminum rod? I'm pretty sure it was aluminum. All right, and then we also had the weights that we put on. We had the weights on the inside. Still pretty easy to turn. You put the weights on the outside, much harder to get it going back and forth because you were trying to constantly change that rotational motion. And so mass, distribution of the mass affect rotational inertia. What do we use to represent rotational inertia? Well, capital letter I for rotational inertia. Also called moment of inertia or inertial moment, but we'll use the term rotational inertia. We said if you wanted to change a body's rotary motion, you would have to apply an outside torque, not necessarily just an outside force. That force would have to be in some way, some component of the force would have to be, what is torque? It's force applied perpendicular to radius. I get that down. Torque is force and radius. Force applied perpendicular to radius. So if the force is in no way perpendicular to a radius at the point of contact, there will be no rotary motion taking place. The force must have some perpendicular component to the radius at the point of contact. So force times radius, when they are perpendicular, is torque. Torque is measured in what units then? Newton meters or pound foot. Pound foot, the other way around for torque. Newton meters or pound feet. Let's see. Law of torque. The law of torque. Kind of ties in the idea of what we talked about with causing rotational motion, right? The more rotational inertia something has, the more torque it takes to cause it to rotate or to change its rotation. And then the amount of change you want to cause, right? If I want to only speed something up a little bit, it doesn't take as much torque. If I want to speed it up a lot more, in its spin rate, if I want to change the spin rate, what we said change in spin rate is called? Angular acceleration. And we said the rotational inertia is affecting that. So tau equals I alpha was your law of torque. Tau equals I alpha was the law of torque. We used tau equals FR, write that equation down for torque as well. Tau equals FR to solve torque problems. We had multiple torques acting at the same time on a body. We said there are two directions of torque, two types of torque. Clockwise and counterclockwise. Do you remember doing those problems? Somewhere back in your memory, like, oh yeah, we had all the clockwise and all the counterclockwise. And we said that they had to equal each other and problems like that. So clockwise torques and counterclockwise torques. If they balance out, we have what's called equilibrium, specifically rotational equilibrium. When the sum of all the clockwise torques equals the sum of all the counterclockwise torques. If all the forces also balance, and that's what we had in our problems, the forces and the torques balanced, we have translational equilibrium, forces balanced, rotational equilibrium, torques balanced, therefore we had static equilibrium. And the forces and torques are all in balance. Some key equations to get down. I actually already gave you a couple of key equations there. Tau equals FR and tau equals I alpha. Let's get down some others. I'm going to list these in order. You need to know the equation for angular velocity. Omega equals theta rad. That's that angular displacement over t. Remember, angular displacement measured in radians, time measured in seconds, so angular velocity measured in radians per second. We also need to recall that 1 revolution equals 2 pi radians when doing calculations like this. Remember, the revolution is 2 pi radians when we do calculations like this. So if you're given revolutions per second or revolutions per minute or this many revolutions in this much time, maybe a revolution in half a second, right? Remember that revolutions are 2 pi radians. I believe I already had you write that down. Remember, if I wanted the linear, that's the angular times the radius. Usually we would do that with linear velocity. Usually we do that to find linear velocity. You could do it with linear acceleration as well. We just didn't very often. This was the main time we said linear equals angular times radius. Also, angular acceleration, remember, is the change in angular velocity per unit time, the change in the spin rate. Omega sub f minus omega sub I over t. We said that I was equal to m, the mass, times the distribution of the mass squared. I equals mr squared. Now, that's a general equation. There's exception to that, of course. It depends on the shape. But for any particle, mr squared, of course, usually we had some fraction of some kind there. We said that tau, you already wrote this down, wouldn't hurt to write it again. Tau equals FR or tau equals I alpha. We talked about as an object moves forward, it has motion. An object in motion is what kind of energy, class? Going all the way back to last semester. If it's moving forward, it has kinetic energy, right? Kinetic energy. Well, if an object is spinning, it has kinetic energy. It has rotational kinetic energy. Rotational kinetic energy, remember, was 1/2 I omega squared. But we looked especially at the kinetic energy total for something rolling as well. And we said if an object is rolling, it has the 1/2 mv squared of its forward linear motion, translational motion, plus it has its rotational kinetic energy as well. And so for a rolling object, we had this equation. I just want you to get this one down because it includes both linear and rotational. And that is chapter 13. Everyone is now scared. The good news is the whole test is in chapter 13. All right, but do spend some time there. That probably is where you need to spend the most time. Because I've got a feeling as soon as I go to chapter 14, you're going to remember this stuff better. Kids, you just do, for some reason. Chapter 14, we started talking about the energy, kinetic energy, if you will, of the atoms and molecules within a body, within an object. What do we call this? Internal kinetic energy. Thermal energy. Thermal energy is the kinetic energy of an object's atoms and molecules. What do we call the measure of thermal energy? Temperature. Temperature. The transfer of thermal energy, heat. If two objects have the same thermal energy, then there will be no flow of thermal energy. There will be no heat, and therefore we have what's called? Two objects have the same thermal energy. Thermal equilibrium. We measure thermal energy. We measure temperature using a thermometer. We use one of three temperature scales. What are the three temperature scales?
Celsius, Fahrenheit.
Celsius, Fahrenheit, Kelvin. Which one? Scientists don't use it no more. Fahrenheit, right? Scientists are the only ones who use Kelvin. Most of the world uses Celsius or centigrade. What is the reference point for Celsius and Kelvin thermometers? Triple point of water is how they're calibrated based on that temperature. The Kelvin scale is unique because no negatives, meaning its lowest temperature is 0, and we call that. What would absolute 0 be on the Celsius scale? It's way down there. Oh, did you say it at the end? Negative 273.15. Okay, I was like, wait, did he say 273.15 negative? I was like, did he say negative at the end? And I just missed it. Negative 273.15 degrees Celsius would be absolute 0. Anyone remember what it would be approximately Fahrenheit? About negative 458. You don't have to know that. I was just curious if we remembered. Let's see here. What do we call the lowest obtainable temperature theoretically? It's never been done, but theoretically the lowest possible temperature is called absolute 0. That is that 0 Kelvin, or that negative 272.15. We talked about temperature conversions. I'll get to that when we get to the equations. We said that as an object heats up, what happens to it? Molecules get excited. They start moving more. And because they move more, the object gets bigger, right? Objects will expand as they are heated. Objects will expand as they are heated. And there is one substance that will expand at one particular point of the cooling process. What is that one substance? Water. And water doesn't necessarily expand as it cools. It only expands specifically as it is freezing. At that time, while it is freezing, it will expand. If it continues to cool, the ice will contract back down again. But it will expand while it's freezing. Why is that important?
So fishies don't die.
So fishies don't die. How does it keep fishies from dying?
Because it sinks down, and then when it freezes,
It would sink
it goes
down.
back up.
Oh, okay. So the water as it is freezing, and the cold air is what freezes it, of course. As the air touches the water, as it freezes, it expands. So rather than contracting and falling, it forms that shelf of ice, which doesn't crush everything below it, and somewhat keeps the water beneath it from being as cold as it could be. Also, it's good for playing ice hockey up north. If any of you have ever been up north to play ice hockey, you're like, what's hockey? For all our northern friends, we don't get ice in Georgia, at least not more than enough to make the roads dangerous, and then we stay home and drink hot cocoa and watch movies, because we all get out of school when it freezes the roads. We don't know what to do. Anyway, speaking of roads also expand, right, as they heat up. And this is what causes the cracking and stuff in roads, unless engineers are smart and they leave little rubber barriers or even metal grooved barriers in bridges called expansion gaps. You don't have to know that term, I was just curious. Expansion gaps. I was staring at a picture of it, that's what brought it up. So objects expand when they are heated. There's three factors that affect the thermal expansion of an object. Okay, the type of material, right? What is the substance? Its coefficient of expansion is going to make a difference. The original size of the object. How long is it to begin with? The longer it is, the more it can expand, right? The smaller it is, the less it has the capability of expanding. Cross-sectional, that would be for area expansion. Temperature change, right? If thermal energy is what makes it expand, or heat is what makes it expand, then the change in temperature, of course, will cause greater expansion. So again, type of material based on the coefficient of expansion, the original size, whether that's length, area, volume, whatever, and the temperature change. Which state of matter experiences the most dramatic expansion? Gas. Which one experiences the least? Solids, right? We're looking at solid expansion because that's something we can see. It's harder to see liquid and gas expansion, but so we were looking at solid expansion, but we also noticed in our math really wasn't that much expansion was there as we looked at the solids. We talked about the transfer of energy, this thermal energy class. We said we call it what again? Heat. Transfer of thermal energy is called heat. We have 3 different units for heat, and it's not Fahrenheit, Celsius, or Kelvin. Joules, calories, BTUs, kilocalories, just 1,000 calories, that's not separate. BTUs, joules and calories. Which one of those is defined as the amount of heat necessary to raise the temperature of 1 gram of water 1 degree Celsius? That's a calorie. Which one is defined as the amount of heat necessary to raise the temperature of 1 pound of water 1 degree Fahrenheit? BTU. And which one isn't really defined by water changing its temperature? Joule. Rather, the joule is already predefined. How many joules in a calorie? 4.18. If we looked at a person or a body or an object, maybe this bottle of water, how much heat is necessary to raise the temperature of that bottle of water 1 degree Celsius? Class I'm talking about? Heat capacity. The temperature to raise an object, or the heat necessary to raise the temperature of an object 1 degree Celsius is heat capacity. Now, if I just wanted to raise a gram of that water 1 degree Celsius, that would be class specific heat. We already said that for that would be a calorie or 4.18 joules. We said if you add enough heat to an object that is a solid, some solids reach a point, if you add enough thermal energy, add enough heat, that the molecular structure breaks down and the object will cease to be a solid and actually turn into a liquid. Melting metals, for instance, melting down plastics, melting wax, as we saw yesterday for the making of those industrial pencils Michael's coloring in his notes with. Anyway, it's like, I have a new pencil, I must use it, or wax marker, grease pen. Anyway, so if you can, the heat necessary to change a solid into a liquid is called the heat of, or latent heat of, fusion. If you wanted to vaporize a liquid, cause the liquid to turn into a gas, we have what's called the latent heat of vaporization. An object that allows thermal energy to flow through it, or heat to move through it, is called a object that allows heat to flow through. Thermal conductor, a thermal conductor. Something that does not allow heat to flow through it is called a thermal insulator. Again, we use the word thermal because when we talk about conductors and insulators, we think of electricity first. So to mention that we're specifically looking at heat or thermal energy, thermal conductor or thermal insulator. We talked about 4 ways in which heat is transferred or heat flows from one body to another. If the temperature is, for instance, in the winter time, right? It's not winter here. It is, but it's not. It's supposedly winter for 2.5 more weeks, but it felt like summer recently because it's the South. It's what we do. We only know it's spring because there's pollen. Anyway, but anyway, bemoaning life in Georgia. So in the winter time, right? And it's cold outside, so we come inside, and our home is nice and warm. Well, that's because for many of us, there are electric coils that get really hot, and air is blown across the coils, and it blows throughout the house, and it makes the house nice and warm. We are warmed by those coils, or by the air, rather, that moved off of the coils. The air carried the heat from the coils to us. We call that method of heat transfer class convection. Now, if you really wanted to heat by conduction, and I don't recommend this, you'd have to do what, Michael?
You'd have to touch the coil.
Touch the coils that are very hot. Bad idea, okay? Bad idea. You'd get too much heat in one spot at one time. Your skin wouldn't be able to handle it, and you would get what's called a burn. Excessive thermal energy. You excited the molecules too much, and they cooked. All right, and it's a bad day. Very painful. All right. thermal energy that transfers, or heat that transfers from a very high energy body, potentially even through a vacuum to warm you without necessarily warming the air around, is called radiation. Radiation. Let's get some equations there from chapter 14. First of all, you need to be able to find Celsius temperatures. You need to be able to find Celsius temperatures from Fahrenheit on this exam. So if you're given Fahrenheit, make it Celsius so we can use it, because everything uses Celsius. For instance, the change in length of an object, that thermal expansion, alpha, L sub O, delta T, these have to be in Celsius. By the way, remember, the L sub O is going to both give us our sig figs and our units. We're going to pull sig figs and units from the L sub O. The heat equation, how much heat is necessary to raise the temperature of an object? Well, we take the specific heat, that's the thermal energy needed or heat energy needed per gram. We multiply it by the number of grams and then also by the change in temperature. Specific heat, how much heat needed for 1 gram, 1 degree Celsius. Okay, so multiply by the mass, that tells you how many grams and how many degrees Celsius. Our heat equation. And we use this heat equation in the law of heat exchange, remember. We said we take this hot object, we put it in contact with this cooler object, thermal energy flows until they reach the same thermal equilibrium, right? And so thermal energy lost or heat lost from one is heat gained by the other. The law of heat exchange, negative Q lost equals Q gained. We also have math involving phase change and temperature change that will not be on the exam. So save a little bit of time looking that over. That's chapter 14. Do we feel a little bit better about 14 than 13? Then which one do we need to study more? 13, yes. All right, we skipped chapter 15. We talked just briefly through it. Let's go all the way to chapter 16. We just took a test on this. We should feel really good about chapter 16, okay? We just took a test. We did fairly well. Transfer of energy through an elastic medium is called a wave. And of course, we said a wave has, if it goes up and down, we call it a transverse wave. Now, the particles are going up and down, but the energy is moving forward. The energy goes forward as the particles themselves in the medium go up and down, but the energy is flowing forward. So the particles are moving class perpendicular to wave direction. If particles are going back and forth, like that, then we have a longitudinal wave. Whereas the wave is propagating forward, the particles are going back and forth along that same line. A longitudinal wave. A single disturbance in a wave is called, or in a medium is called a wave pulse. A wave pulse. And it could be an up pulse called a crest, or a down pulse called a, it could be a smushed together pulse, compression, or a spread out pulse, rarefaction, right? Any of those pulses. Now, if you have two of those opposing pulses together, crest and trough, compression and rarefaction class, you have what's called a wave. A wave. Two pulses that are opposing is a wave. If you have a whole bunch of those waves in the same medium, you have a wave train. The undisturbed position of the medium is called equilibrium, and the displacement from equilibrium, either high or low, compressed or rarefacted, that displacement from equilibrium is called amplitude. If you were to measure from one point on one wave to the same exact point on the next wave in a wave train, you have the wavelength. The time it takes for one full wave to pass a given point, period, number of waves per second, frequency, a wave that never weakens but travels in a singular direction. One-dimensional. A wave that weakens slightly as it spreads outward in all directions along a plane. Two-dimensional. A wave that spreads outward in all directions and weakens rapidly. Three-dimensional. A wave strikes the surface and it turns back into the first medium. Reflection. If a wave changes speeds and so it changes direction, we call that refraction. Refraction. The angle at which a wave reaches a boundary or strikes a surface is called the angle of incidence, and it's measured from the normal, not from the surface. We said the law of reflection states that
The angle of incidence equals the angle of the other one.
reflection. The angle of incidence equals the angle of reflection. When waves refract, if they are slowed down by the new medium, they will refract toward the normal. If they speed up, they will refract away from the normal. If a wave, 2 or 3 dimensional wave, spreads outward as it passes through a gap, or it recovers after striking an obstacle, we call this diffraction. Diffraction. Waves collide from opposite directions. They cancel each other out. Briefly, we have complete destructive interference. 2 waves collide from opposite directions. They form a larger wave pulse. Constructive interference. 2 waves collide from opposite directions, resulting in a smaller wave pulse. Destructive interference. Chapter 16, there's only one equation for you to know. V equals lambda F. We did talk about wave speed being dependent on tension and mass per unit length. That won't be on the exam. The only equation from chapter 16 you need is the relationship between wavelength, lambda, and frequency F, and of course wave speed. Should feel really good with chapter 16 just now, right? So 13 and 14 are the biggies. 13 especially is where you're going to want to spend your time reviewing. Chapter 14, spend a little bit of time there. 16 through 18, we should feel pretty good. Let's blast into chapter 17, talking about sound. We said 3 things affect the speed of sound.
Temperature, density, hardness.
Temperature, density, hardness. The only medium, quote unquote, sound can't go through a vacuum, because all media have some degree of elasticity to them, some more than others. We said which factor is the only negative factor? Density slows sound down as you increase it, whereas both hardness and temperature, as they increase, speed of sound increases as well. The sound will speed up. The apparent shift in wavelength and frequency as an object is moving and creating sound. Doppler effect. Doppler effect, that shift in wavelength and frequency. By the way, something I did not mention, this is kind of interesting, I've only actually observed it once, and I don't remember even what the situation was, but I remember observing thinking, oh, that's what it's talking about. There was a little write-up in your textbook on the Doppler effect and how it applies to light waves as well, right? We've established light electromagnetic wave. If a light source is moving very rapidly towards you, you're getting a higher frequency as the light source approaches, right? As you hit those wave fronts, so to speak, more rapidly, you'll tend to see a little bit more of what's called blue shift. The light shifts toward the violet end of the spectrum. So you have a little bit more of a bluish light if the object is moving very quickly towards you. After it passes you, the light you see has a longer wavelength, a lower frequency. You see red, so red shift, blue shift. It's kind of Doppler effect with light, but I've only ever seen it once, and I wish I could remember where I saw something where I'm like, that was weird. But in red shift, blue fish. Dr. Seuss, thank you. Red shift, blue shift of light. Kind of interesting. But again, the object has to be traveling very quickly for you to see that kind of thing. And again, you think, well, okay, like a meteor or something. Well, it's only coming towards you. It's never going away from you, right? Comet, well, it doesn't move fast enough for that to be observed. I don't remember what it was. It might have been like out of the corner of my eye, a car going by me on the interstate. I was like, whoa, that's weird. I just saw the little bit of bluish to reddish shift. I don't know if that's what it was or not. Don't actually look for it, though, on the interstate if you're the one driving, okay? Just focus on the road. But anyway, Doppler effect, we did a lot with that. Obviously, faster than the speed of sound. Supersonic speed produces what kind of wave? The strength of sound is called intensity, but we hear loudness as opposed to intensity. And loudness measured in decibels, intensity measured in watts per square meter. Let's see, the way we perceive audible frequencies. The highest audible frequency we can hear. Highest audible frequency. 20,000 hertz, lowest audible frequency, 20 hertz. Anything above 20,000 hertz? Ultrasonic. Anything below 20 hertz? Infrasonic. Equations from chapter 17. Equations, formulas, if you will, from chapter 17. Don't have to know all of them. You do need to know speed of sound in air starts at 331.5 meters per second. Again, that's at 0 degrees times the square root of the Celsius temperature. By the way, you would need the Celsius temperature for this, as was noted earlier, plus 273 divided by 273. Doppler effect equation, F sub O equals F sub S times V sub air plus V sub O over V sub air minus V sub S. And of course you need to pay attention to direction, right? So the object is moving, if they're approaching, it's positive, away is negative. You're going to practice with all of this in the homework this evening, over the weekend, I guess I should say. You also need to know the equation for intensity as it varies with distance. I1R1 squared equals I2R2 squared. And if you'll remember, though, in class, we generally didn't deal in intensities because that's not what our ear perceives. Again, our ear perceives loudness instead. So in conjunction with this, we need to be able to go back and forth from loudness to intensity. If given a loudness, get the intensity. That gives you intensity, that gives you loudness. And that equation, beta, equals 10 times the log of I over I sub naught. The I sub naught or I sub 0 has a value of 20 negative 12 watts per square meter. Yeah, we're not relying on that and saying 1 sig fig, of course. Just it's easier to enter the calculator that way. That's chapter 7. Did I say 18 a second ago? That's chapter 17. Again, should be a little bit more familiar to you. Chapter 18, last chapter of exam material. Again, the math you're going to practice on a handout tonight. We're going to go over it all in the next lesson, make sure we've got it down really well. Today I want to just hit those terms. Light. We have lots of scientist people, right? Give me one scientist, any scientist, Michael. Huygens. What did Huygens say about light?
He said it's a wave.
He said it's a wave. Give me another scientist.
Newton.
What did Newton say?
They're particles.
Streams of particles. Give me another scientist.
Maxwell.
What did Maxwell say?
He discovered that it was electromagnetic waves.
Good. Said light's an electromagnetic wave. It's part of the electromagnetic spectrum. Another scientist.
Young.
What did Young say or notice? Discover.
Newton is wrong, and he discovered interference.
Good. Discovered interference. Said Newton's wrong. Another scientist.
Einstein.
Einstein. What did Einstein say?
The wave particle. No, the duality.
Wave particle duality. Says light is a wave when it goes through a medium, right? Or transparent medium, I guess I should say. It's electromagnetic wave. When it exchanges energy, it's particles of energy. It's little particles. Or if it goes through a vacuum, it's like streams of particles. Last person.
Herschel.
Herschel's the only one we haven't used yet. What did he discover?
Infrared radiation.
Infrared radiation. Good. Of course, photon is what we call the particles of light now. That's always nice. Speed of light, or really electromagnetic radiation.
3.088 meters per second.
3.0088 meters per second. Different frequencies of light that we can see, we perceive those different frequencies, class, as color. And visible light has 6 basic monochromatic colors in the solar spectrum.
Red, orange, yellow, green, blue, indigo, violet.
Just violet. Yeah, we took indigo out, remember. Red, orange, yellow, green, blue, violet. I hear there's apparently a push to get indigo back in there, but anyway. We'll see. It's like Pluto being a planet. Is indigo really one of the colors of the rainbow? We don't know. Is Pluto really a planet? We don't know. It goes around the sun. That's a very small part of the electromagnetic spectrum. Anything higher in frequency than violet light, ultraviolet, anything lower in frequency than red, infrared. Higher the frequency, the higher the energy. Higher the frequency, the higher the energy. Remember. The highest energy electromagnetic waves? Gamma rays. The lowest energy that we discussed, radio waves. Are microwaves high energy or low energy? Low energy. And then the X-rays are high energy. Primary colors of light.
Red, green, blue.
Red, green, blue. Secondary colors.
Magenta, yellow, cyan.
Magenta, yellow, cyan. You get secondary colors by mixing two primary colors. If you mix all three primary colors,
White.
white. If you mix a primary with a secondary, you could get white if the colors are complementary. If a material does not allow light to go through it at all, we would call the material opaque, meaning one of two things happens with the light that hits it. Light either is reflected or absorbed, right? And how do we tell which color is reflected?
It's the color of the object.
That's the color we see, right? All the other colors get absorbed. We said if you want, say, to not take something that's white, for instance, and you want it to absorb light, you give it a pigment, right? The pigment absorbs all the light except the color you want to see. And so a pigment, it subtracts away colors of light from our view. What are the three primary subtractive primary pigments?
Magenta, yellow, cyan.
And the three subtractive secondaries?
Red, green, blue.
And theoretically, if you mixed all of them, you would get black. There will be no math from chapter 18 on the exam. No math from chapter 18 on this exam. That's chapters 13 through 18. All right? I've given you equations. Tonight you're going to do a handout, which is going to give you practice with the equations. We've got about 7 minutes still. Questions for me? Any questions on anything that we very quickly reviewed? Anything you say, can you go over that again, or maybe skim through your terms real quick and say, hey, can you give me that definition again? Or any questions at all you have for your notes? I guess if you're watching on video, if you're doing it yourself, you can just could have paused and rewound as you went to make sure you got definitions. We know what we need to study. All right, your homework is to complete a handout. As always, it's in the description of the video. 9 problems, similar to what you may see on the exam. And since we're done early, you can go ahead and get a little bit of a head start working on that. And we'll go over this in our next lesson.